So next such measure which we are interested is based on quartile, and that is termed as coefficient of quartile deviation, given by the formula Q3 minus Q1 divided by Q3 plus Q1. So this IQR or quartile deviation, they remain the same for your raw data, discrete data, as well as continuous frequency data, but the method of obtaining your quartile is different. So first you will observe what type of data. Using the particular set of formulas for Qi, you will compute Q1, Q2, Q3. But after computing, whether it is raw data, discrete data, or continuous data, your quartile deviation is always Q3 minus Q1 by 2, IQR is Q3 minus Q1, and coefficient of quartile deviation or coefficient of QD is Q3 minus Q1 divided by Q3 plus Q1. And again, one of the most widely used measure, which is based on standard deviation, is called as coefficient of variation, which is indicated by standard deviation divided by arithmetic mean into 100. And we use a special symbol to indicate the standard deviation, which is sigma, small letter sigma, Greek letter, and we have capital sigma also. We use this capital sigma to indicate the sum or total of a particular column or variable, and this is used to indicate the standard deviation. Now, coefficient of variation is one such measure which is used to differentiate the distribution based on the amount of variation present in the data. Now, if you look into the applications, as said, you will be using this when you're talking about the distributions where the unit of measurements are different. On the other hand, even if you have the distributions where unit of measurements are same, they doesn't, lead you to different conclusions. So they widely use this for all the cases. So whether you're comparing distributions with same unit of measurement or comparing distributions with different unit of measurements, they always compute this measure, and that is abbreviated as CV, and it gives you the variation in the data, or it answers the question what percent of X bar is your sigma. So that question, the answer is given by CV. If you just remove the percentage sign, just to make the comparison very easily, we convert that decimal number into percentage. But if you want to keep that as a decimal number itself, then we just call the sigma by X bar as coefficient of standard deviation. So you can say coefficient of standard deviation expressed as a percentage is coefficient of variation. So both will lead you to the same. So just a multiplication by 100 is missing here. Both gives you the same measure as well as the same case. So these are about the relative measures of the three. And the fourth case, we talked about mean deviation. So we have three types of mean deviation: mean deviation from mean deviation from median, and mean deviation from mode. And for each of those cases, we can obtain the relative measure. If you are using the deviation from mean, then we call that as mean deviation from mean. And for that, the coefficient or the relative measure is defined as ratio of mean deviation divided by the measure, which is mean. Now, both will have the same unit of measurement, they get cancelled. Now, similarly, you can talk about coefficient of mean deviation from median, coefficient of mean deviation from mode, and they are defined similarly. So this will be mean deviation from median divided by median, mean deviation from mode divided by mode. Okay, so this was the section and analysis of univariate data, where we talk about much of the available formulas. And I'm not skipping any of these cases, as said, because your paper will be set by the university or a person who has, just a little knowledge of statistics. He just look into the syllabus and the questions will be framed. So I can't take a risk of skipping any of these. So we'll look into the calculations, and at the time of calculations, so again, I'll be revising the formulas. So if you have missed out certain formulas can just go with the calculations. Okay, so these are the measures. So we have covered three set of measures till today: measures of central tendency, measures of position, and measures of what we call as position, sorry, variation or spread. The fourth measure is measures of skewness and kurtosis. Measures of skewness and kurtosis. Now, skewness and kurtosis are also, certain properties which are observed in the data. And again, as said, these are all just additional measures whenever you are in a dilemma of selecting the distribution. If you are in a situation where you can't see or you can't differentiate the distributions based on the already computed measures, then we need extra. So have distribution, all the measures like mean, median are also same. You are computing standard deviation, that is also same. Quadratic deviation is also same. So that could happen, and that is a very rare case. But if that happens, so again, selecting which is a good distribution, that problem remains there. So to answer that, we look into the skewness as well as kurtosis. Let us understand what is the simple meaning of the skew. Skew or skewness. Skew means deviate, fluctuate towards one end. So the skewness could be simply called as asymmetry or lack of symmetry. So you're partializing your data is such that it is supporting only one part of the magnitude of the variable. That is your high set of values which are very high, set of values which are very low. In that case, we say we are observing skewness in the data. Now, to understand this, it is very easy to look into the frequency polygon or frequency curve of the data. So we know how to generate the frequency curve. So we'll take the values of x on the x-axis, frequency on the y-axis. We mark the pair x and f, and we join this using the smooth curve, and the resultant curve is called as frequency curve. So even you can, observe this particular curve whenever you are dealing with your histogram also. So histogram also on a whole, gives you the shape of the curve observed for a particular distribution. So using this graph, we can talk about skewness. So if you have a frequency curve such that it is what called as bell-shaped, that is, it is symmetric. What is the meaning of symmetry? If you divide any shape in the middle, and if you observe that one is the mirror image of the other, then we say such curves to be symmetric. So this is a symmetric curve. So whenever I say symmetric, that means there is no skewness present in the data. So whenever we say skew, as said, you will have very large set of high values or larger number of low values. If that happens, the shape of the curve will drastically change. So if you have very low values, you have only minimum number of low values, but set of high values are very large compared to low values. Like say 2, 4, 6 as the low values, I have only 3 cases. But when I look into the larger values, much of that larger values are present in the data. So if this happens, then you can observe that the frequency distribution is like this. Whenever we talk about a curve, we talk about two important parts of the curve called as tails as well as peak. So this left and right extreme are called as tails of the frequency distribution or frequency curve, and this is called as the peak of the distribution. So if you're worried about how the stretch is varying on either tail, then you're talking about the property called as skewness. If you're worried or if you look into what is happening to the peak, whether it is a very sharp peak like this or it is a flat peak or a moderate peak, and also we look into the thickness of the tail. In that case, we talk about what called as kurtosis. So the skewness property tells you whether a distribution is symmetric or not. If you observe the distribution to be symmetric, we call such curves and such distributions to be symmetric distributions. What is the property of the symmetric distribution? You will observe the middlemost value, which is median, and statistically will observe x bar as well as z to be the same value. So first type of skewness is zero skewness or no skewness, zero skewness or no skewness, where left tail is equally stretched an amount same as the right tail, or you call that as symmetric curve or distribution. Now, do we have to always draw the frequency curve to observe that? No. So we got an answer. If you observe for any set of data, all these measures, mean, median, mode are same, or in a practical situation, you could have very closer values, very closer values. Even in that case, we say the distribution is symmetric. And the other property of this symmetric data is that if you look into the quartiles, this is my Q3, this is Q1 median, and this is Q2, this is Q1, then the distance between the quartiles. So if I say what is the distance between Q2 and Q1, that is Q2 minus Q1. What is the distance between Q3 and Q2? That is Q3 minus Q2. So if this happens, or you could say that Q3 minus Q1 is equal to 2Q2. So both of this will lead into this. In that case, also we say the distribution is a symmetric distribution, and we call quartiles are equidistant. So how far Q2 is from Q1, the same distance is observed. How far is Q3 from Q2? So both that is same. In that case, we say quartiles to be equidistant. Or in a practical situation, you could observe that they are very much close. And in that case, we say there is no skewness. So we are observing how can we quantify this. So here we are just understanding the property, but what is the exact amount of skewness? So can we compute this skewness and quantify that as a number? So we can use these properties in order to come up with the measures. So we'll talk about measures later. We'll look into the types of skewness now. So this is the first type, zero skewness or no skewness, which is also called as symmetric distribution or symmetric curve. What are the important properties? Your curve is symmetric. That is, if you divide the curve exactly in the middle, left will be the mirror image of the right and vice versa. All the three important measures of central tendencies, mean, median, mode, they became numerically same, and your quartiles are equidistant. So these are the important properties of a zero skewed distribution. And the next case is left skewed distribution. Left skewed distribution. So here we observe the skewness to be present in the direction of the lower set of values. So you can clearly observe where you have low values and high values, and where is the concentration. So if much of the values are concentrated on the left part, that is on the lower part of the distribution, which are the low values magnitudely speaking, so in that case we say there is left skewness. So what happens when you have a left skewness? What happens to the measure? Now the mode is always a measure with respect to highest frequency. This is also a frequency distribution. So you have X, you have F. So I have come up with a curve like this. But when you look into mode, mode is the value of X with highest frequency. So whenever you have highest frequency, then you observe the peak. So from the tip of your curve, if you draw a straight line and if you observe what is the value of X there, that X will always produce you mode. And since you have low values, much of the low values present in the data, your X bar gets attracted towards that low value. So you'll observe X bar somewhere here, and in between those two, not exactly in between, so somewhere between your mode and your mean, median will be there. So if you are observing a left skewed distribution, then in that case, mode is large compared to mean. Mode is larger than mean. And again, if you look into the quartiles of a left skewed distribution. So you will have somewhere here Q1, Q2, Q3. If you look into the case, the distance between Q2 and Q1 is larger than smaller than the distance between Q3 and Q2. Let me just check that. Q2 minus Q1 should be larger than this. Okay. So whenever we are observing the left skewness, we'll have Q2 value observed closer to Q3. So this happens with respect to the quartiles. So just by observing the numerical values of mean, median, mode, as well as the quartiles, you can say whether the distribution is left skewed. Now this left skewed distributions are also called as negatively skewed distributions, because when you compute the actual measure of skewness using the formula, you will observe negative sign in the final value. So if any skewness measure is leading to a negative value, the skewness is called as negative skewness or left skewness. Negative skewness or left skewness. And the next and the last type of skewness what we observe is right skewness, and this is also called as positive skewness because the measure produces a positive number. Every property is opposite in comparison to the left skewed distribution. So you'll observe concentration, much of the data values will be larger. You will have a peak, in the beginning only. So you will observe mode first, then median, then mean. So your mode is lesser than mean. And if you look into the quartiles, the opposite of this happens. So somewhere here you will have Q1 and you will have Q2 close to this. Q3 will be somewhere here. So the distance between Q3 and Q2 will be larger when we talk about a right skewed distribution. So this is an important property. So you could have a theory question as well as a problem from this. Whereas in most of the other cases, measure of central tendency, position, as well as measures of spread, can expect simple definitions, but numerical problems will be there. But here, the skewness, types of skewness, explanation, how do you identify the measures based on central tendency, based on quartiles, and what is the definition and types of skewness. So a theory question is possible, and also a problem on the measures of skewness is also possible. So we have understood skewness, but we didn't come across what is the amount of skewness, to what extent the distribution is skewed. Can I capture this measure of capture this property of skewness using the measure? So that is answerable, and we have a measure called as measure of skewness and two basic categories. There are many other methods based on deciles, percentiles, etc. And two simple methods are the one given by the person called as Carl Pearson and the other one called as Bowley. So they have given much of the contribution in the field of statistics. So again, here also you can come across with the measure of skewness as well as the measure of coefficient of the measure. So he defines skewness just by observing the values of mean and mode. So what we said, if I have a symmetric distribution, x bar, m and z are same. If I have a left skewed distribution, right skewed distribution, I'll have mode, I'll have mean. So x bar is greater here. If I have a left skewed distribution, I'll have x bar here and z here. So x bar is less than z. So just by looking into the values of mean and mode, you can say what type of skewness. If they are equal, then your x bar minus z will be equal to 0. So a value of Karl Pearson skewness equal to 0 is indicating this situation, which is a symmetric or 0 skewness. So since this value comes out to be 0, we call this as 0 skewness. Now coming to the second case. So here it is a right tail distribution, or I could say a right skewed distribution. So value of x bar is larger compared to mode. So when you obtain x bar minus z, that will be greater than 0. So that's why we call right skewness as positive skewness. So here mode is larger, mean is smaller. So when you compute x bar minus z, you will observe a negative number, negative value. Therefore, this type of skewness is called as negative skewness. But when we look into the definition of mode, mode could be ill-defined sometimes. So in that case, he come up with an alternative formula which is based on the median. So whenever you are unable to find a single value for mode, then you cannot talk about skewness based on the mode because mode doesn't exist. So in that case, he said you use median instead of that. And the reason why he said use median, because in most of the data, he observed that your mean, median, mode are related by the formula mode is equal to 3 median minus 2 mean. Mode is equal to 3 median minus 2 mean. Therefore, if you apply this formula in place of z here, that gets simplified to 3 times of x bar minus z. And as said, you can use this in comparing the skewness of the distribution with the same unit of measurement, because your x bar, your zm carry the same unit of measurement. But if you are in a situation where you want to compare the skewness of several distributions where unit of measurements are different, in that case, we gave the formula to be x bar minus z by standard deviation, or 3 times of x bar minus median divided by standard deviation. So this gives you a unit-free measure which could be used in comparing the skewness of the various types of distribution. But if you look into the disadvantages of this method or formula, it is using your x bar, it is using your z. Z is sometimes ill-defined, but we have overcome the disadvantage by introducing median. But there is no guarantee that every time your z will be equal to 3 median minus 2 mean. So this happens when your n is large and you are observing some skewness present. So in most of the cases happens, or practically speaking, approximations will be observed, but theoretically there is no evidence to derive this formula. So hence we say this is not much applicable. And also if you look into the x bar has an influence of extreme values on them. So if you have very low values, very high values, just a single high value, single low value will fluctuate this value of x bar, altering the result of your standard deviation, mean, and all other formulas based on mean. Therefore, many persons argued that it is not suitable in all cases, and the best measure which is suitable is called as Bowley's skewness. He said your central measures like mean, median, mode are sometimes not easy to observe. They are fluctuated by extreme values. So he said instead of using the measures of central tendency, you just use the quartiles, because as said, even just by looking into the values of quartiles and the distance between quartiles, we can say whether the skewness is right or left. Therefore, Bowley said instead of using measures of central tendency, use the skewness based on quartiles, and he named after himself, called as Bowley's skewness. And if you want to compare them with different distributions, he also gave a formula for coefficient of skewness, and that is Q3 plus Q1 minus 2Q2 divided by Q3 minus Q1. And the conclusion is same. So as said, in case of symmetric distribution, I said the distance or the quartiles are equidistant. So if symmetricity happens, then Q3 minus Q2 is same as Q2 minus Q1. If you send every term to this side, you will get Q3 plus Q1 minus 2Q2. So if this is equal to this, then this will be equal to 0. So a value of Bowler skewness equal to 0 indicates the symmetric distribution. On the other hand, if you are observing the positive value for this, indicating the right skewness, and for positive skewness, so we say our Q3 minus Q2 is larger than this, so Q3 plus Q1 minus 2Q2 will be greater than 0, and a skewness value less than 0 indicates the negative skewness. Now, often, students make some confusion with respect to the formulas available on quartiles. So we talk about three important measures based on quartiles: IQR, skewness, and quartile deviation. IQR is just Q3 minus Q1. Quartile deviation is Q3 minus Q1 by 2. And if you further go and see what is coefficient of quartile deviation, that has the same term, but if you look into skewness, there you have Q3 minus Q1 in the denominator, but in case of coefficient of QD, Q3 minus Q1 is in the numerator, the sum is in the denominator. So don't get confused. So just look into the formulas. Okay, so I'll end the session here. So I have another class this week allotted. So I need one more hour in this week because I'll be stopping at this point of time today. So if possible, maybe within this week or even on Saturday, Sunday is also fine. But before next week, I need another hour where we can solve some numerical problems on all these measures and understand the measures better. Okay. So if you have any doubt, you can ask. Please discuss among yourself and let me know when will you give me an hour. And preferably, I need that in the afternoons, after 3, even at evening 6, 7 is also fine. You discuss and you let me know. Okay, so if you have any doubt, you can